function is, when we will look at some of the initial results needed to set it up. But I think the best thing to do at the very beginning is to just look at an example. Okay, so Fourier series are a method or concept which are used a lot in signal processing, and it provides a kind of standard way of representing functions and picking out interesting features about signals and sound signals or signals in images and so on. Okay, so the example I'm going to show you, just to kind of, okay, we won't appreciate much of the technical detail here yet, but we'll just get a good visual illustration of what these things are. So the basis function, the function that we're dealing with here is a very simple function. It's called the square wave function. This is shown in red. It's only shown in the domain between -pi and pi. And I'll put a link to this demo in the comments after the lecture recording as well. And it's kind of like the Heaviside step function. So it's 0 on the negative half of the interval and +1 on the positive half of the interval, going from -pi to pi. Now, in this setting, the functions we're considering, we consider them to be periodic. So this square wave function will continue across the whole of the domain, just repeating this behavior here, which we see between -pi and pi, repeating that periodically over the whole real numbers. So from +pi up to 2pi, it would be 0 again, and then from 2pi up to 3pi, it would equal to 1 again. Then it'd be back down to 0 for another pi, and back up to 1 for another pi. So that's why it's called a square wave. It's like a wave, but it's just completely square. And it just oscillates between the value +1 and 0. Saying 0 for an interval of pi, then jumping to +1 for an interval of pi, and then jumping to -1 for an interval of pi, and so on. Okay, so this is a basic kind of wave or signal, very simple wave or signal, and it's often crops up as an initial example in signal processing. Now, what a Fourier series is it's a way to get a very different representation of that function and see it as an accumulation of standard signals. So the standard signals, if you like, or the standard functions, or a word we'll use more when we explain some of the mathematical setting to this, is basis function. But the basis functions, or standard functions that we're going to use here, are all the sine functions. So it's actually true. So what you're seeing here is what's called a Fourier series for the sine wave, for the square wave function. It's presented here as a finite sum. So it's the sum from n equals 1 up to m of all these sine parts. Okay, so you've got the sine function evaluated at 2n minus 1 times x. So this is an odd multiple of x. Okay, so these sine functions are only some of the large collection of basis functions that feature in Fourier series, but they're the only ones that feature in this square wave example. This is what it looks like. There's a constant term of a half out here, factor 2 over pi, and you're summing up from n equals 1 up to some value, and this combination of sine functions. And this can be illustrated here in the graph. So we've got this little slider here. So the slider is, which is currently set at 0, the slider is the number of terms in this sum. Here. So at the moment it's set to 0. So at the moment we're just looking at the value of half. If you think about it, the best way of approximating this square wave function, if you're only allowed to approximate the square wave function with a single constant, the best constant to use would be a half. It's the average behavior of the square wave function over the whole interval, and it's the best one, it's the best one number summary of the whole function. And as you increase the number of terms, so if we go to one term, we see here is the best way to approximate this square wave function with a single sine function. Okay, it's sine of it's 1 over, well, it's just sine of x. It's just sine of x, but it's rescaled by 2 over pi and added to the half constant that we had before. So you can see that this sine function does a slightly better job at estimating or approximating the red function than the single constant did. Single constant kind of had the average behavior of the function, but now when you introduce one sine function, you know, we're oscillating around the function a bit better. So this is a Fourier series approximation to the square wave function, but only featuring two terms, a single constant and a single sine function. As you bring in more and more sine functions, remember the sine functions, they're evaluated at sine of some increasing odd multiple of x. So the sine functions you're bringing in have a higher frequency. So they oscillate more, they go through more oscillations inside the interval minus pi to pi. So here is with m equals 2. So we got the constant 1/2 and 2 sine functions. Okay, so now we've got much tighter oscillations around the square wave function. And our combination of standard basis sine functions is doing a slightly better job at approximating the square wave. And as you keep on increasing this parameter m, bringing in more and more sine functions of higher and higher frequency, you see we start to get a very good approximation to the square wave function indeed. And if you boost it right up to, say, 10 terms, you see now that the blue function, this combination of sine functions, is doing quite a good job of approximating the square wave function. And if you boost it up to something silly like 30 or something, that appears. So it's an extremely good approximation now to the square wave function. Across most of the domain, the Fourier series is doing a very good job of approximating. Very tight oscillations around the objective function. Now there's something funny happening at these points, but these points, there's something funny happening anyway. The point 0 here is a point of discontinuity in the original function. So you can see that causes a breakdown in the approximation because the Fourier series, which is a continuous function, so it's a combination of sine functions, a linear combination of sine functions. For a continuous function to make this sudden change in value is quite a task, so that shows the kind of breakdown of the approximation close to the point of discontinuity. But anyway, this is just something visual to look at the start, an illustration of what a Fourier series is. So in this example, the Fourier series is the blue function, and it's a way to approximate this standard signal of the square wave function, but approximate it in quite a different way with the family of using some of the functions from a large family of standard basis functions. Okay, so what exactly are these Fourier series, and how should we think about them? Well, I'm going to switch to the overhead now, because before we consider that formal definition in the notes, I just want to kind of make some introductory remarks about well, some motivational remarks that will connect this idea of a Fourier series to things you already know about. Okay. It's important, I think, when you're meeting new concepts like this to kind of connect them back and see examples of where they're coming from. So this is the Fourier series chapter, and just some background motivation. Background and motivation for it. So we'll kind of think back and think of some other things that you already know about, which will, which you should help you to draw connections between these things you already know about and these new concepts of Fourier series that we're going to introduce. Okay. So first of all, I'd like you to recall the concept of a Taylor series. Taylor series for a function. So we have a function f going from the real numbers to the real numbers. And for certain well-behaved functions, so the well-behaved, I mean, we won't go too much into the technical details, but the well-behaved nature here is that the function is continuous, it's differentiable, you can differentiate it any number of times, and its derivatives are all continuous and so on. So for certain well-behaved functions f, we have the Taylor series. Taylor series for f, which is a way to represent the values of the function in a standard kind of way. And the standard way is as a kind of infinite polynomial in the argument x. So I've left a gap there. So the Taylor series is quite simply an infinite polynomial representation of the function f. Okay? Now the coefficients come from the various derivatives of f evaluated at 0 here, divided, each one divided by m factorial, where m is the index in the summation. And this will be valid in a certain region around the base point 0. Again, for different functions, for some functions, this Taylor series will be valid across the whole of the domain, the whole of the real numbers. For other ones, it's only valid in a certain interval around 0. That's dependent on the function f. Okay. But some important points about it is it allows us to represent the function f in a standardized way. So if suddenly you can represent all the functions that you're dealing with, you can represent them all as polynomials, albeit infinite polynomials, suddenly it allows you to kind of treat them all in the same kind of way. If you develop techniques for dealing with polynomials, such as how to integrate and how to differentiate polynomials, and how to study those, then suddenly you've got some kind of standard way of attacking all functions, for most functions. But secondly, from a more kind of pragmatic viewpoint, you can approximate the value. If you aren't dealing with exact values, if you're, whatever your application is or whatever the context is, if you're happy to deal with approximations, then taking some finite initial part of this sum, so I'll just label the summation star. So if you take some finite initial part of the sum star, this provides an approximation. An approximation to the value f of x. And the idea is, of course, as you take in more and more terms of the Taylor series, the approximation gets better and better. The Taylor series are important for just implementing the evaluation of functions into computers and calculators. Now, I don't think it's exactly Taylor series that are used, but in some cases it is, but perhaps maybe some other related kind of representations for functions. But if you think about it, when you ask your calculator what sign of some argument is, or you ask the computer what sign of some argument is. Well, if you think about it, I mean, how in the world does your calculator know what the value of sign of some argument is? Because you think about it, fundamentally, calculators, computers, they're very, very basic. All they can do is add ones and noughts together, right? All they can do at the bottom ground level, all they can do is do binary arithmetic. Now they can do it very fast, of course. But only being able to do binary arithmetic isn't that much of a handicap when you think about it. We can represent all numbers as binary representation. So then you can add any numbers together. And you can also multiply any numbers together, because multiplication you can think of as just repeated addition. So the basic circuitry can do arithmetic operations of addition and multiplication with numbers. Well, what Taylor series allow you to do then is to, you see, because all that's involved in evaluating a polynomial, if you know what the coefficients are, if you pre-computed the coefficients and stored them, built them into the design of the calculator, so to speak. All that's needed then to evaluate the polynomial, well, to evaluate a polynomial, you're just adding together different terms, and calculating these x to the power n terms is just multiplication. So Taylor series show you how it could be possible, using only basic arithmetic operations of addition and multiplication, to nevertheless approximate arbitrary functions. And by taking more and more terms, getting a better and better approximation to the value of the functions. Okay. Now the reason I'm showing you this is Fourier series act like this too. Okay? Fourier series give you a standard way of representing functions through an infinite sum, not this time an infinite polynomial sum, but now an infinite linear combination of sine and cosine functions. And secondly, they also have this feature that if you take some finite initial part of the summation, you get an approximation to the function. And the more and more terms of the series you bring in, the better and better the approximation gets. So Fourier series, when we finally meet the formal definition and we see exactly what they are, we will notice that they exhibit these properties too. Okay, but I'd like to say some other things as well, and these remarks concern linear algebra. This Fourier series, although they're quite an analytic thing, we're dealing with functions, and we've got infinite series converging to the value of a function, so it's kind of, it seems quite a very analytical concept. But it does make use of, and it is an example of, and it connects with a lot of linear algebra concepts as well. So we'd also like to remind ourselves is some facts about linear algebra. Okay, so that's the other half of this unit that you've been doing with Stephen, continuing on from your first year work. But Fourier series is a place where the kind of two halves of the unit and the two parts of mathematics, linear algebra, and some concepts and analysis, where they kind of join together and feed off one another. Okay? So in linear algebra, we have this idea that a vector space has a basis. Okay, any vector space has a basis. Okay, and any vector from the space. Any vector from the space can be represented as a linear combination of the basis vectors. Any vector from the vector space can be represented as a linear combination of the basis vectors. And this gives you, it's nice to think of it this gives you a standardized way of representing vectors from the space. Okay, you just describe all vectors as a certain linear combination of some standard basis vectors. So for example, in R3, we have the standard basis E1, E2, E3. These standard basis vectors you're familiar with. These three vectors, they're all zeros except one in the first, second, or third position. And any x from R3 is written, you can write your x as lambda 1 times E1 plus lambda 2 times E2 plus lambda 3 times E3. And so the lambda 1, lambda 2, lambda 3 are the components of the vector x with respect to the basis. That's the kind of terminology that you use. And how are the individual components? How can you show how the components are defined in terms of the vector and the basis vectors? Well, there's this nice property that the component lambda I is the dot product of the vector with the basis vector from our standard orthonormal basis. Okay. So not every basis has this property where the components are just given by dot product with the basis vectors, but nice, special, nice bases do, where these bases are orthonormal. Okay. Each of the basis vectors has length 1, magnitude 1, and they're all mutually perpendicular. Okay. In that case, then you have this nice kind of pleasing symmetric relationship that the component of a vector is simply the dot product of the vector with the basis vector. So that's a basic example of some basic concepts of bases and dot products and the relationship between them all in the vector space. And so now let's finally meet the concept of a Fourier series. So Fourier series fit into this picture. Fit into this picture. Fit into this picture of having a vector space and a basis for it. So I'm starting to connect back with some of the material in the notes now. But I'll just wipe this out. So the vector space, so we consider a vector space of certain, and for certain, this will mean well-behaved in a sense, certain well-behaved functions from the real numbers to the real numbers. Now we'll see shortly what conditions we want for this well-behaved. Okay? But certain kind of nice functions, they'll have to be periodic. That would be one of the main tasks of them. So the first thing to appreciate is that if you gather a lot of real-valued functions together, that they can form a vector space. Okay? Because you do have vector type operations of addition and scalar multiplication. Okay? If you're given any two functions, you can add the functions together, and that gives you a third function. If you have any function and a scalar, you can multiply the function by the scalar. Okay? And then you've got a new function. It's just a rescaling of the previous function. You just multiplied all its values by some certain scalar, but it's a new function. Okay? So the space of functions has vector type operations, natural vector type operations ready and waiting there. The addition of functions and the scalar multiplication of functions. It will turn out that this vector space has a basis. This basis is going to be this set I'll call B for the moment. Consists of the constant function 1 and an infinite collection of sine and cosine functions. Okay? So there's this set B of functions. It's got the constant function 1, cosine of nx for every integer value n, positive integer value n. So n is an integer and it's greater than or equal to 0. And also the function sine of n times x. Okay? So it will turn out that this set B, that B is a basis for this space. And so any function f from the space can be written. So this is what, sorry, can't see that. This is what our Fourier series looks like. Okay, so we'll see this kind of expression over and over again. Now, for reasons of kind of standardization and fitting in with other formulae, the constant term we represent as half times this coefficient A0. So that's the constant term of the Fourier series. So this is a multiple of this basis function. Yeah. So this 1 up here is representing the constant function of value 1. So this term half of A0, this is some scalar multiple of that constant function. Then you've got an infinite linear combination of cosine functions and a second infinite linear combination of sine functions. And this choice of notation, an for the coefficients of the cosine functions and bn for the coefficients of the sine functions, this is quite traditional notation to use in this area, and it's quite common. You'll see that same A and B notation being used in most texts that you look at. So we're going to see that we can think about this in a very linear algebra type setting. We've got a vector space of functions, certain well-behaved functions, and we'll describe what those conditions are shortly. We'll have an infinite set of certain special standard functions from the space. This is going to be an infinite basis for the space. Constant function 1, all of these cosines and all of those sine functions. And then they allow you to express, so this equation I've written down here is very much to think of it in terms of an equation like this. So here you've got any vector from the space being written as a linear combination of the basis vectors. Well, this is exactly what's going on here, except we've got any vector is now one of these functions. And instead of lambda 1, e1 plus lambda 2, e2 plus lambda 3, e3, it's now an infinite linear combination. Okay, but it's still various coefficients, half a0, an, bn, multiplied by the various functions from the basis for the space. Okay. Now, you might ask, what's the corresponding thing to the dot product? So before, in the simple R3 example, what connected the vector x to the coefficients that crop up in the linear combination, well, those coefficients can be described as the dot product of the vector x with the appropriate basis function. The corresponding thing in the language of Fourier series is a certain inner product, it's called. Have you come on to inner products yet with Stephen? Yeah, he's just started that section, I think. Okay, so the basis B is now, I don't think, yeah, it's not an orthonormal basis. So it's not the nicest kind of basis you can have, but it is an orthogonal basis. Meaning that all the elements in the basis, all these different functions are mutually orthogonal, or mutually perpendicular in a sense, as defined by, not by the normal dot product of vectors. We don't have the normal dot product of Euclidean vectors in this setting, but we do have an inner product which is going to play the same, or play a similar role. So this basis B is an orthogonal basis with respect to the inner product. So this inner product, I'll write it like this, square brackets, sorry, these angle brackets. So it's a generalization of the concept of a, that you already know about, of a dot product. So a dot product between normal Euclidean vectors, this is kind of a continuous generalization of that. So rather than multiplying together corresponding components of a vector and adding up those individual products, we do the continuous version of that, which is we integrate together the product of the two functions. And of course, integration is the continuous analog, or the continuous version of discrete summation. Now we only integrate over the interval minus pi to pi. This, as when we go through the formal definitions, you'll see that the setting, the initial setting for all of this is just based on the domain minus pi to pi. Minus pi to pi is the kind of fundamental domain of the sine and cosine functions. The sine and cosine functions are both periodic at a period 2 pi. Okay, so if you know their behavior across the interval minus pi to pi, you can see their behavior across the whole domain of the real numbers, because they just repeat themselves across the rest of the real domain. So where you saw the dot product playing a role between a vector and its components in the Euclidean vector space setting, we're going to see a very similar thing happen, except this time we got an infinite basis of these sine and cosine functions and the constant function. Our vectors are now functions, and in place of the dot product we have this thing called an inner product, which is a way of taking two functions from the space and producing a scalar. Because what kind of object is the integral? Okay, well, the integral is an instruction or an operation telling you to carry out something, but the value that the thing has when you evaluate it is just a number. Okay, so it does act like the dot product of vectors in that respect. Takes two vectors from the space, does something with them, and produces a number. Okay? So this is an example of an inner product on a different kind of vector space. Okay, so with those introductory remarks in our minds, so that was to kind of remind you of some things you already know about, and kind of give you set you up with some ways to think about these. Well, now let's look at some of the initial definitions in the notes. Okay. Okay, so if we look here at the first page of the chapter, so we got the definition of Fourier series. So we're describing this as a theorem because it gives you the conditions on the functions that are in the vector space of functions. Okay. So this theorem assumes that f from the real numbers to the real numbers is a periodic function of period 2 pi. So that means you can think of the function as having a certain kind of behavior in the interval minus pi to pi, but then that behavior is simply repeated over the rest of the real numbers. Okay? So over the interval from pi to 3 pi, is the next interval of length 2 pi, the function f will just repeat exactly the same values that it went through on the interval minus pi. So the function is periodic of period 2 pi. There's some technical, so these conditions here are the well-behaved conditions that I had in the notes before. So our functions, they mustn't be too strange. They can only have at most a finite number of discontinuities. But they can have discontinuities. Like that original square wave function I showed you at the beginning had a discontinuity at the point x equals 0, because at x equals 0, it made a sudden instantaneous jump from the value 0 up to the value 1. So it's a point of discontinuity. So our functions can have any finite number of discontinuities in this interval. I mean, it would have to be a fairly pathological function, very badly behaved function to have an infinite number of discontinuities in the interval. But we won't be considering those. And also, we're only going to allow our function to have at most a finite number of maximums and minimums within this basic interval of minus pi to pi. Again, any function which has an infinite number of maximums and minimums inside a finite interval is a pretty badly behaved function, so to speak. Okay. So what the theorem says then is that there do exist a set of coefficients, A0, A1, A2, an infinite set of A's and an infinite set of B's, B1, B2, etc. And these coefficients allow you to say that the value of the function f is given by this infinite linear combination of the constant function and the sines and the cosines. Okay, so that's what the theorem is saying. If the function is well behaved, in the sense of those conditions above, periodic, finite number of discontinuities and maximums and minimums, then there will exist all these coefficients which will allow you to say that the function is exactly this infinite linear combination of the constant function and the sines and cosines. Well, at least at points of continuity of f. Okay? Now, f might have points of discontinuity. So at points of discontinuity, the value of the infinite linear combination won't necessarily be, well, it won't be the value that the function takes at the point of discontinuity. But what it will do the next best thing. The value of the infinite linear combination will be the average behavior of the function either side of the point of discontinuity. Okay, so f at xd plus and f at xd minus, these are the two limits, the two limiting values of the function as you approach the discontinuity from either side. And the infinite series will give you the average of those two, half of the sum of those two. Now, that can be a bit difficult to kind of parse or untangle everything that's saying. So all that's saying is, if we go back to our initial example of the square wave function, notice that it's always the case that at the point of discontinuity, the Fourier series, which is the blue function, that takes the value a half at the point of discontinuity. So our original function, maybe it takes the value 0, or maybe it takes the value 1 at the point of discontinuity. We're not so interested in what its exact defined value is at 0. But what's clear is that the limiting value as the original function approaches the point of discontinuity from the right, that limiting value is 1. The limiting value as you approach 0 from the left is 0. And the Fourier series always goes through the point half at x equals 0. So you can see that from the very first simplest Fourier sum, just a single constant, where we're using the constant a half to estimate the function there. As you bring in more and more sine terms, the Fourier series is always going through exactly a half at the point x equals 0. And that property is preserved no matter how many terms you allow into the Fourier series. Kind of difficult to see there because it's going so steeply down. You can see it's to the right of the y-axis here, and then it crosses the y-axis at half, and then it's to the left. Okay. So that's just an example, an illustration of this behavior here in this statement 3.2. Okay. At the point of discontinuity, Fourier series takes the average behavior, the average of the limiting behaviors of f either side of the point of discontinuity. Okay, so this series of sines and cosines, this is what we call a Fourier series for the function f. Okay? And a basic problem, so the theorem tells us that these Fourier series exist. So a basic kind of initial task we'll be faced with is, given a certain function, obtaining its Fourier series. So that kind of problem will be, given a certain function f, obtaining these coefficients a0, all the a's, the a1, a2, a3, and the b1, the b2, and the b2. Okay? The coefficients are what define a particular Fourier series for a particular function. Okay? So we have this idea that this, okay, I've called it f here in the notes, but we have this family of functions which are going to be a basis for the space. Okay? So these form an orthogonal basis for the infinite dimensional vector space of functions satisfying the conditions in Fourier's theorem. So you collect together all those functions that satisfy the conditions in Fourier's theorem. They form a vector space. And this inner product here, so this tells you how to take two functions here written as phi and psi in the space. You integrate their product across the interval minus pi to pi. That's going to give you a scalar value. That's going to be an inner product on the space. Okay? And this is what will allow us to obtain the Fourier series. Okay. Now there's some examples here, some initial examples and properties, and this is what we're going to work through next time. So the first thing we're going to do is we're going to prove this property, or prove the various parts of it, that the basis functions are orthogonal with respect to this inner product. So there's an example 3.1 here. So show that the functions, so show that if you take a cosine function and a sine function, show that they are orthogonal with respect to the inner product. So that means when you take the inner product of these two functions, the cosine and the sine, you must get 0. There's lots of other parts to that. If we take the inner product of any two different cosines or any two different sines, we'll again expect to get the value 0 and so on. So that's some of the things we'll deal with next time. And we'll just end today by looking at the Fourier series formulae, the formulae for the Fourier coefficients. So this will be what we'll spend, this will be the main subject of the next lecture. So just to remind you, just to show you the simpler thing to think about, remember the R3 example. Any vector x can be written in terms of those three standard basis functions. And the coefficients, the coefficient lambda I for the vector x with respect to the basis vector ei is given by the dot product of x with the basis vector. Okay, you're all familiar with that. The equivalent thing to that, the corresponding statement to that, in the setting of Fourier series, are these equations here. So these remember the, yeah, you can see it there. The A0 and all the ANs and all the BNs, those are the coefficients of f in the infinite linear combination of the sine and cosine functions. So this A0, all the ANs and all the BNs, they're the equivalent of the lambda 1, lambda 2, lambda 3 in the R3 example. And the equivalent thing to the dot product of x with one of the basis functions are these coefficient formulae here. Now they're expressed here in terms of integrals. With these integrals here, you see you're integrating f of x times the cosine of n times x. Here you're integrating f of x times the sine of nx. So those integrals of products of functions, those are examples of this inner product. Okay. So these Fourier coefficient formulae show you how you get the coefficients an for any particular value of n by taking the inner product of the function you're dealing with, f, with the basis function cosine of n times x. You integrate that from minus pi to pi. Now our basis family here is not orthonormal, it is orthogonal, so it isn't just the inner product on its own. We do have to rescale it slightly. There's a scaling factor of 1 over pi. So this scaling factor is present in all of them. But really, if you neglect that for the moment, or don't consider that, you see the coefficient as the value of the inner product of the function with one of the basis functions. So this collection of functions here is more complicated, all right, continuous, but this is the corresponding thing to that simple idea that the coefficient lambda I was the dot product of x with the basis function, with the basis vector ER in the simple R3 setting. So in the more complicated infinite dimensional vector space setting of Fourier series, these equations here are the corresponding thing. Okay, so we'll be concerned with justifying these next time as well. Okay. All right, then I'll leave it there for this morning. I appreciate it's mostly introductory stuff. There's not too many problems opened up from that. You may find some of the initial tutorial problems you can do now, but we'll make more progress with that in the lectures next week.